again. Okay. So x, what is the domain of this function? Right, it's a friendly function. This one is friendly and nice. I'm going to use the same numbers, tiny ones around 0. Please plug them in and give me the y values for each. Yes, indeed, when we raise a fraction to a negative number, indeed. 4. Very good. Very good. Okay, 1/2 and? Very good. Can anyone conclude about this way? Very good. Can anyone conclude here? Very good. Perfect. So can anyone give us the first ordered pair from left to right? Excellent. Next ordered pair. Very good. Next ordered pair. And of course, y equals 0, horizontal asymptote at infinity only, of course. Yes, of course. All exponential functions, no matter what the base is, the pure ones have to pass through 0, 1. And then you're going to say 1/2, and then I get in trouble because I don't know how to plot those. They're too small.
Close enough.
So this is 1/2 to the x. What can you say about this function? And the answer is a lot.
It's always decreasing.
Always decreasing on all its domain. So I like to say to my students when they ask in the middle of the semester, they haven't done much, they haven't done homework, they haven't come to class, and so on and so forth, and they say, hey, professor, can I still get a good grade and pass your class? And my answer is yes. As long as your grade moving forward follows an exponential function with a base greater than 1, which has the highest growth rate possible, I'll say definitely. Definitely not an exponential function with a base less than 1, because you don't want that, right? Okay, perfect. So it's a decreasing function on all its domain. Is it 1-to-1?
Yes.
Doesn't have an inverse.
Yes.
Very good. Let's graph the inverse. We know nothing about it. We will in the next 20 minutes. What is this? Yes, every time I graph the function and its inverse on the same coordinate system, I have to graph y equals x. Can anyone give us a couple of points so I can graph this inverse? 4, -2. Perfect. It's you mean 1, 0. Okay. 2, -1, I agree. Remember, when the function crosses y equals x, the inverse must cross at the same point. Mandatory. If the function doesn't cross y equals x, the inverse will not cross y equals x. But if the function crosses at this point, the inverse must cross at the same point. So this is f inverse. And the base has to be 1/2 as well. Otherwise, it's not going to work. Any questions? Any questions? Okay. I think we had the idea about transformations. Would you like to use another function, look at another function with transformations? Maybe of this. Okay, very good. So let's say, let's graph 1/2 raised to x minus 2 and -2. And what is the base function here? Very good. It's the exponential function 1/2 raised to x. The first transformation is 1/2 raised to x minus 2. What does this do to the base function? Right 2. Awesome. And number 2 is 1/2 raised to x minus 2 and minus 2. What does this do to number 1?
Down to.
Down 2, very good. It's not outside here. It's this function minus 2, so it has to be down 2.
So if there's a value in front of the one,
Then it's a
then
different
it's a
story.
string.
Yes, yes. Because you have to apply that first. In order of operations, you will have to multiply by this and then deal with that.
Yeah. Okay.
In order of operations. Are we okay
That's
with
why
this
I'm
one?
getting confused.
Yes? Okay, perfect. So now I have to graph the exponential function 1/2 to the x. That's our first step. But I have to ask myself, how do I graph it? Do I graph it as a increasing function, or do I graph it as a decreasing function on all its domain? Right, because the base is less than 1. Very good. It has to cross at 0, 1. So here's the graph. So 1/2 raised to x. Then you told me to shift it 2 units to the right. This is our point. This all we need. Please shift this 2 to the right and tell me where it lands. 2, 1, indeed. So here's the graph of 1/2 raised to x minus 2. Final transformation, what do we need to do? But I can't. Not before the horizontal asymptote. The horizontal asymptote was at y equals 0. Where do I shift it to? Very good, awesome. And now that's all I need. I need you to tell me where this point is moving, and I will shift the whole thing. Excellent. Again, I have no idea where it crosses. I'm not interested. Whatever. I need to identify the shape, and this is final. And can anyone give us the range of this function? Right. So please remember, the exponential function, the pure exponential function will always have domain or real numbers, and the range is 0 to infinity. But once we apply transformations to it, anything can happen. Not about the domain, but about the range. Okay. Questions? 4.2, log functions. We already graphed them. This is the log function with the base less than 1/2. And a few minutes ago, this is the log function with the base greater than 1. But what is more important now, before we graph them again, is this. Please give me an exponential function, any exponential function you want to work with. And I also need 3 numbers, 1 positive, 1 negative, and 0. Any exponential function you want to work with.
I guess we can do 2x.
You want 2 to the x? Oh, let's do 3 to the x this time, just to be different. And please pick a positive value, a negative value, and after you do that, I would like you to identify the y coordinates.
We're gonna do 3 and negative 3.
Okay, 3, let's say a negative 4. Okay, so tell me what the y value will be. 27, very good. Bless you.
Thank you.
Very good. Not 0. Any number raised to 0 is 1. And this one, it has to be a fraction because the power will be negative, right? 3 to negative 4 is 1 over 3 to the 4th, which is 1 over
Oh, okay.
81. I claim now, this is my claim, and you should say, show me. Even if you don't, I will still have to show you. I claim that the inverse function has to have the same base. I know this is going to look intimidating. Please don't. It's just a function. So log base 3 of x. How do we read this one more time? log base 3 of x. It looks out of this world. It's just a function. Log base 3 of x. What do I have to prove to you now? I have to prove to you that when we apply this function to 27, we get absolutely. Otherwise, it's not the inverse function. When we apply this function to 1, I have to show you that we get, of course. And when we apply this function to 1 over 81, we get, otherwise the whole thing fails. Before I do that, however, we have to, for a minute, talk about the most important concept in this chapter. That's by me. Maybe others will not agree. So the most important concept in chapter 4. First, I'm going to write it in plain English. The most important concept. Here's why I think it's the most important. Nothing happens without this concept. No word problems can be solved. No equations can be really addressed easily. Everything revolves around this concept in this chapter about exponential and log. In plain English first, any log equation can be replaced or converted, whatever you want to write, can be replaced by an exponential equation, comma, and vice versa. So if I have a log equation, I can change it into an exponential equation. If I have an exponential equation, I can change it into a log equation. Any log equation can be replaced or converted into by an exponential equation and vice versa. Okay, I'll come back to this. Now in mathematical terms, this is what we write. Log base A of x is y. This is a log equation. This symbol means that I can start here and get this, or vice versa. I can start here and get this. It's called the double equivalency symbol. Now, I would like us to, for a moment, don't do anything and just watch. It will only take 3 seconds, I promise. We always start with the base and we go counterclockwise. The base raised to y, not a times y. A raised to power y equals x. And this is the exponential equation. I consider this the most important concept of this chapter, that any log equation can be replaced by an exponential, and any exponential can be replaced by a log. With this in mind, I can go back and we can apply log base 3 to 27 and see what happens. We can apply log base 3 to 1, see what happens, and log base 3 apply to 1 over 81 and see what happens. Ready? So, log base 3 apply to 27. I have no idea what this is. No clue. No clue. But I know that this is equivalent to, can anyone help here? Dictate. We start with the base. 3 raised to whatever, I have no idea, equals 27. But we know there is only one number because log and exponential are all 1 to 1, both 1 to 1. So I can't say, maybe it's this, or maybe it's that, or maybe it's this. No, there's only one answer. Only one number we raise 3 to get 27. And that number must be, that's it. So therefore, when we apply log base 3 to 27, it definitely returns 3. Next one, log base 3 of 1. I have no idea what this is, but I know that I can easily change it into something I know. and that is 3 from the base, counterclockwise. 3 raised to blah blah equals 1. But there is no ambiguity here. I can find 2 or 3 or 4 numbers. There is only one that I raised 3 to get 1. Only one, yes. So this is 0. That's why when we apply log base 3 to 1, it indeed returns 0. Finally, we want to apply log base 3 to 1 over 81. Log base 3 to 1 over 81. Have no clue, but that's okay because I can change it into something I know how to solve, which is 3 to whatever equals 1 over 81. Well, I know that that whatever must be a negative number for the result to be a fraction. And which number? It's just only one. Negative 4 indeed. Because only 3 raised to negative 4 will be 1 over 81. So now we can say for good and for forever, in other words, the same thing. So I can say this, that 1/2 to the x has which inverse function? It has to be a log. It has to have the same base, which is of x. What if I ask now log base 12 of x? And I'm asking you, what is the inverse function? Right, of course. The base has to be the same. If they are to be inverses of each other, they have to have the same base. And before we look at the graph, of course, we do have two special log functions. What do you think they're called? Common and, of course, common and natural. What will be the base of the common? And there is no ambiguity. It must be the same. Yes. This is the only one we do not write the base for. If you see a blank for the base, you must remember it's common log. And the natural, what would be the base for the natural? Yes. And this is the second one we do not write the base for. We write ln. ln. It should have been NL, natural log, but it comes from German, so that's why it's log natural. Very good. So this is the natural log function. This is the common log function. They are so special that they share the same key with their inverse functions. As you see here, 10 to the x and log. They share the same key. They're inverses of each other. As you see here, the ln, natural log, and e to the x, they're inverses of each other. They share the same key. Of course, I was going to damage something. Any questions? Any questions? Okay, so let's go back to the graphs. Since we graphed them, let's look at the two shapes. Log functions. I'm going to graph them both, and you'll tell me which one has the base less than 1. And of course, as I said, these are not friendly functions. We have to worry about them a lot. Here's one, and here's the other. Of course, they are both log, base a of x. But let's identify the base in the first one and the base in the second one. Remember, if it's decreasing, the base must be less than 1. If it's increasing, the base must be, yes. So here is a base greater than 1, and here is the base between 0 and 1. A tiny positive base and a positive base greater than 1. Of course, the base function has to cross at 1, 0, always. If it has transformations, it's a different story. Okay, does this function, since it has domain 0 to infinity, does it have a vertical asymptote? Yes, of course. X equals 0 is the VA. Here it is. It approaches infinity. It approaches negative infinity. That's the characteristic, typical, right? Typical for a vertical asymptote. At least one side goes to either infinity or negative infinity. Okay, so I would like us to look at some domain. Domain questions. Problem 76 on page 490. Yes, we can apply some transformations on those, and we'll do that in a minute. F of x log base 5 of x plus 6. Now, here's a question before we look at the domain of this function. I don't see Ln, which is base e, and I don't see Log, which is base 10. I see base 5. How do I address this if I want to graph it? Some calculators, there is a way. It's called the change of base formula. But some calculators, I don't know if the software does that. Okay. It does. So the calculators I have, I don't care for this feature, but the calculators I have does not allow me to put, calculators I have do not allow me to put the base I want. But some of your calculators, these older models do not, which is fine. It's a very simple change of base formula, very simple. You don't need that. I don't use it, I never do, to tell you the truth. I always use the base change of base formula, and I will show you that. Okay, so here we're not asked to graph. Here we're only asked to find the domain of this function. Now let me refresh your memory. I'd like us to connect the concepts. When we had this function that I know no one likes, what did we do? What did we write to find the domain of this? Exactly. In the same way, I have to address that. However, 0 is allowed here, but not here. So what is log applied to? Log is applied to this quantity, like the square root was applied to this quantity. Therefore, x minus 2 had to be greater than or equal to 0. Now it's applied to this quantity, so then x plus 6 has to be strictly greater than 0. And then x greater than negative 6, so the domain is negative 6 to infinity, and the vertical asymptote is, yes, but I have to write x, right? It's vertical. X equals negative 6. Now, I'm going to just change because I don't want to present, in the next section, we're going to present all the properties of log, including the change of base formula. So, don't forget about this, and let's say it's natural log of x plus 6, and I want to graph it. It's a transformation. It has one simple transformation in it. I'm trying to connect the dots again because let's say we have f of x equals natural log of x plus 6. There is only one transformation. What is the base function? Base function here. Yes, of course, natural log. And then the first transformation, and the only one, is this. Where does it go? What am I trying to do here? What is it? Of course, left 6. That's it. So when I graph the function, do I graph it increasing on all its domain or decreasing on all its domain, the base function? Right, because it's natural log, and that is 2.7. So here is the base function at 1, and this is the natural log x. And remember, it has a vertical asymptote. When we shifted up and down functions with a horizontal asymptote, what did we do first? Right, but now I'm shifting left and right functions with a vertical asymptote. What do I have to shift first? Right, where will I shift it from y equals 0? Exactly. 1, 2, 3, 4, 5, 6. Where does this point our marker? That's all I care about. 1 point. Yes. So here's the graph. So this is natural log of x plus 6. Look at the domain we determined. No one can look. Look at the domain we determined. Negative 6 to infinity. Right? So initially, if I were to ask you, does this function cross the y-axis? And you say, of course not. But does the new function cross the y-axis? Yes, when x is 0. And that would be natural log 6. Everything changes when transformations are involved. Any questions? I did not consider 4.1 finished, but I do consider 4.2 finished. I do consider 4.